The first speaker of this conference today, Professor Naoya Ando. The topic of this talking is nilpotent structures of oriented neutral vector bundles. Yes, please.
Thank you very much. It is my great pleasure to express my cordial gratitude to the organizers of International Scientific Online Conference, Algebraic and Geometric Methods of Analysis, for giving me an opportunity of this talk. I will talk about nilpotent structures of oriented neutral vector bundles. In the first section, I will explain the space-like twistor spaces and the time-like twistor spaces. In section 2, I will explain the light-like twistor spaces. These are analogs of the space-like twistor spaces and the time-like twistor spaces. I will explain the definition of nilpotent structures in the case a given vector bundle has a rank 4. In section 3, I will explain the general definition of nilpotent structures of an oriented neutral vector bundle of rank 4n. In section 4, I will explain the Walker condition. The Walker condition is derived from the definition of Walker manifold. This condition is related to a metric connection of the bundle, vector bundle. In section 5, I will explain K-nilpotent structures. K-nilpotent structures are special nilpotent structures, and I will explain the main theorems. Let M be a manifold and large E an oriented vector bundle over M of rank 4. And H a neutral metric of E, then H has signature 2, 2. Then the twofold exterior power of E is a vector bundle over M of rank 6. Rank 6. And just a moment. Sorry, rank 6. And H hat, let H hat be the metric of the twofold exterior power induced by H. Then H has signature 2, 4. We have a bundle decomposition like this. These subbundles has rank 3 and they are orthogonal to each other with respect to H hat. The restriction of H hat on each subbundle has signature 1, 2. In these subbundles, sorry, just a moment. Sorry. In these subbundles, we consider such fiber bundles. Notice that this is 1. These fiber bundles are the space-like twistor spaces associated with E. Each section of a space-like twistor spaces corresponds to a complex structure of E, preserving H. This means that H is Hermitian with respect to a complex structure. Let nabla be an H connection of E. Then nabla is a connection of the vector bundle with satisfying this condition. Then nabla induces an H hat connection nabla hat of the twofold exterior power of E. In addition, nabla hat gives connections of these subbundles. Then we have this proposition. A section omega of a space-like twistor space is horizontal with respect to nabla hat. This means that nabla hat omega vanishes. If and only if the corresponding complex structure I omega of E is parallel with respect to nabla. In these subbundles, we also consider such fiber bundles. Notice that this is -1. These fiber bundles are the time-like twistor spaces associated with E. Each section of a time-like twistor space corresponds to a paracomplex structure of E, reversing H. A paracomplex structure is a bundle endomorphism satisfying J, 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 and paracomplex structure is defined by these conditions. And this reversing H means that H is para-Hermitian with respect to this paracomplex structure. Then we have this proposition. A section of a time-like twistor space is horizontal with respect to nabla hat if and only if the corresponding paracomplex structure of E is parallel with respect to nabla. In these subbundles, we also consider these subbundles. Notice that this is 0. These fiber bundles are the light-like twistor spaces associated with E. Each section of a light-like twistor space is locally represented like this. Notice that this epsilon and this epsilon. Notice this epsilon and this. This small e is a suitable ordered pseudo-orthonormal local frame field of the neutral vector band, giving the orientation of the band. We suppose E1, E1, E1 and E2 are space-like. So E1, E2 satisfies these conditions. While E3, E3 and E4, E3 and E4 are time-like. So E3, E4 satisfy the second condition. And omega plus 1, omega plus minus 1 and omega plus minus 3 are defined by this. A section omega of a light-like twistor space with epsilon is locally represented like this. We call such a frame field as small e an admissible frame field of a section omega. Let small f be another admissible frame field. Then the relation between E and F is given by this. Notice that this epsilon and large A is an element of SO2 such that there exist B and C like this. A is represented by the product of B and C. In general, an element of SO22, in general, an element of SO22 is represented by the product of B and C. B is given by given in the form, and C in general, C is in the form of C prime. C prime is SO12. This is general situation. In particular, the relation between E and F is given by this relation, and A satisfies. A is given by these B and C. Let large lambda 1 is a square matrix of degree 4 defined like this. Notice that this is minus 1. Then we obtain this proposition. An element A of SO22 satisfies this condition. A and lambda 1 are commutative. If and only if there exists BC as above, satisfying this relation. Therefore, omega, a section omega of a right-like twistor space with epsilon defines a bundle, the bundle endomorphism N by this. Notice that this epsilon for an admissible frame field of omega. We call large N an epsilon nilpotent structure of EH, corresponding to a section omega of a right-like twistor space with epsilon. We can define epsilon nilpotent structures of EH without sections of right-like twistor spaces. A bundle endomorphism large N is called an epsilon nilpotent structure of EH if on a neighborhood of each point of M there exists an ordered pseudo-orthonormal local frame field, small e, giving the orientation of the vector bundle and satisfying this. Let large N be an epsilon nilpotent structure of EH. Then such a frame field as E in definition 2 is called an admissible frame field of N. Noticing this proposition. We see that omega, large omega in this. Large omega does not depend on the choice of an admissible frame field of N. This means that an epsilon nilpotent structure large N defines a section of a right-like twistor space with epsilon. Hence, we obtain a one-to-one correspondence between the set of sections of the right-like twistor space with epsilon and the set of epsilon nilpotent structure of EH. For an ordered pseudo-orthonormal local frame field small e, giving the orientation, small e is an admissible frame field of a section of the right-like twistor space with epsilon. If and only if small e is an admissible frame field of the corresponding epsilon nilpotent structure of EH. In addition, we obtain this theorem. A section omega of the right-like twistor space with epsilon is horizontal with respect to nabla hat. If and only if the corresponding epsilon nilpotent structure n omega of EH is parallel with respect to nabla. In this section, I will explain the general definition of nilpotent structures of an oriented neutral vector bundle of rank 4n. For a positive, sorry, just a moment. Sorry, my computer is freezed. Just a moment. Just a moment. Okay. For a positive integer n, we define a square matrix large lambda n of degree 4n like this. Notice that this signature. If n is equal to 1, then this lambda 1 coincides with this lambda 1. We also define a square matrix of degree 4n, I prime 4n epsilon. Like this. If epsilon is equal to plus, then I prime 4n plus is the identity matrix. On the other hand, if epsilon is equal to minus, then I prime 4n minus is slightly different from the identity matrix because of this. Sorry, because of this. Let large E be an oriented vector bundle over M of rank 4n, and H a neutral metric of E. We call a bundle endomorphism large N an epsilon nilpotent structure of EH if on a neighborhood of each point of M, there exists an ordered pseudo-orthonormal local frame field small e, giving the orientation of the vector bundle and satisfying this. We suppose that these are space-like, and the others are time-like. This definition 3.1 for n equal to 1 coincides with this definition. This definition coincides with this definition for n equal to 1. Let large n be an epsilon nilpotent structure of EH. Then such a frame field as small e is called an admissible frame field of M. Let large b, sorry, let large b large G, sorry, let large G be a Lie subgroup of SO2N2N defined like this. An element G, an element of G is just an element of SO2N2N satisfying this condition. A and lambda n are commutative. Then small f is an admissible frame field of N if and only if for an admissible frame field small e of N there exists a G-valued function A satisfying this condition. For an admissible frame field small e of N, we set this Xi given by Xi1 wedge, Xi2 wedge, wedge, Xi2n, where Xi1, Xi2n are given by these. Notice that these signature, these are minus, and these are plus. Then we obtain this proposition. Xi does not depend on the choice of an admissible frame field small e of N. Therefore, an epsilon nilpotent structure N gives a section Xn of the 2n-fold exterior power of the vector bundle E. If N is equal to 1, then this is a section of the right-like twistor space with epsilon corresponding to N. And this omega coincides with this omega. We obtain this proposition. A bundle endomorphism large N is an epsilon nilpotent structure of EH for epsilon equal to plus or minus. If and only if N satisfies these two conditions, the image of N coincides with the kernel of N. And if we set this, then pi n is a right-like subbundle of EH of rank 2. And n satisfies this for any local section phi of the vector band. From this proposition, we see that an epsilon nilpotent structure N gives a null structure on each fiber of the vector bundle E. This is seen from condition A. And H is null Hermitian with respect to N. This condition, this is seen from condition B. And the subbundle pi n, is locally spanned by Xi1, Xi2. These 2n local section of the vector band. In this section, I will explain the Walker condition. The Walker condition is derived from the definition of Walker manifolds. Let nabla be an H connection of E. Then nabla is a connection of E satisfying this. Let large N be an epsilon nilpotent structure of EH. Then we say that N satisfies the Walker condition with respect to nabla if pi n is parallel with respect to nabla. In other words, if for any local section psi of pi n, nabla psi is one form valued in pi n. Let nabla hat be the connection of the 2n-fold exterior power induced by nabla. Then we obtain this proposition. An epsilon nilpotent structure large n satisfies the Walker condition with respect to nabla. If and only if nabla hat Cn is represented like this, the tensor product of one form alpha on M and Cn. If n is parallel with respect to nabla, then nabla hat Cn vanishes, and therefore n satisfies the Walker condition. Even if n satisfies the Walker condition, it is possible that n does not satisfy this condition. There exist such examples of epsilon nilpotent structure. If n is equal to 1, then this condition is equivalent to this condition. This is already stated in this theorem. If n is equal to 1, this condition is equivalent to this condition. On the other hand, if n is more than or equal to 2, then this condition does not necessarily mean this condition. There exist examples of epsilon nilpotent structures satisfying this and this. This is not zero. The Walker condition is derived from the definition of Walker manifolds. A pseudo-Riemannian 2n manifold, even-dimensional manifold, equipped with an n-dimensional distribution D, is called a Walker manifold if D is parallel with respect to the Levi-Civita connection. In this section, I will explain K-nilpotent structures. K-nilpotent structures are special nilpotent structures. Let large n be an epsilon nilpotent structure of EH, and K, large K, are the subgroup of SO2N2N. Then N is called a K-nilpotent structure of EH if there exists an open cover U lambda of M and a family E lambda, small E lambda of admissible frame fields of N satisfying these two conditions. Each small E lambda is defined on U lambda. And if the intersection of U lambda and U mu is not empty, then we have this on the intersection. For a k-valued function A lambda mu, then we immediately obtain this proposition. Any epsilon nilpotent structure of EH is a G nilpotent structure of EH. This is seen from this is seen from this fact. The relation between two admissible frame fields of an epsilon nilpotent structure is given by a G-valued function. So we obtain proposition 5. Let large n be a k-nilpotent structure of EH and small e an admissible frame field of n defined on an open set of U of M. Then we call small e a k-admissible frame field, k-admissible frame field of N. If for small lambda with this, there exists a k-valued function A lambda satisfying this. Any admissible frame field of an epsilon nilpotent structure is a G-admissible frame field. Let nabla be an H connection of E. Then N is called a K-nilpotent structure of EH nabla if there exists an open cover U lambda of M and a family small e lambda of admissible frame fields of N satisfying these two conditions. These two conditions the above conditions 1, 2, and the third condition. The connection form omega lambda of nabla with respect to this local frame field is valued in the Lie algebra of K. Then we obtain this proposition. A G-nilpotent structure of EH nabla is just an epsilon nilpotent structure of EH, parallel with respect to nabla. Let large I be a complex structure of E and J1, J2 paracomplex structures of E. Suppose that these satisfy this relation. Then I, J1, J2 span a subbundle E, I, J1, J2 of and E of rank 3, which is called a paraquaternionic structure. In addition, suppose that a neutral metric H is adapted to Eij1J2. That is, I preserves H and J1, J2 reverse H. We said that H nabla I J1, J2 form a neutral hyperkähler structure of E. If these satisfy not only condition 1 and condition 2, but also the third condition. IJ1, J2 are parallel with respect to nabla. Let large H be a Lie subgroup of SO2N2N defined like this. A11, 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 A21, 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 A31, 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 A41, 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 A41. Then H is a Lie subgroup of G. We obtain this theorem. A section of this quaternionic structure given by this NR theta R, small r, complex structure I minus sine theta paracomplex structure J1 plus cosine theta the other paracomplex structure J2. For small r are non-zero real number small r and theta in this interval is an H-nilpotent structure of EH. If these form a neutral hyperkähler structure of E, then NR theta is an H nilpotent structure of EH nabla.
5 minutes left.
Okay, okay.
Okay.
In addition, we obtain this theorem. Let N be an epsilon nilpotent and H nilpotent structure of EH. Then there exists a unique light-like subbundle pi star n of EH of rank 2n, which is locally spanned by Xi1 prime, Xi2n prime. These 2n local section. Notice that these are plus and these are minus. While これだ。Xi1 is given by E1 minus E2n plus 1. Similarly, Xi is given by EI minus E2n plus 1. And Xn plus 1 is given by En plus 1 plus epsilon E3n plus 1. Xn plus I is given by En plus I plus E3n plus I. Notice these signature. Small e is any H admissible frame field of N. From this setting, we obtain this bundle decomposition. There exists a unique epsilon and H nilpotent, epsilon nilpotent and H nilpotent structure N star of EH, such that each H admissible frame field of N star is given by E prime. For an H admissible frame field small e. Notice that these signatures. In particular, we obtain this. Pi n star is coincides with pi star n. If n is an H nilpotent structure of EH nabla, then n star is also an H nilpotent structure of EH nabla. Let N be an H nilpotent structure of EH. We call N star, as in the above theorem, the dual H nilpotent structure of N. Then N is the dual H nilpotent structure of N star. We obtain this corollary for an H nilpotent structure N of EH. If we set this, then J1, J2 give a paraquaternionic structure EI J1, J2, such that H is adapted to this. In addition, if N is an H nilpotent structure of EH nabla, then these form a neutral hyperkähler structure. Let large I be a complex structure of E and J1, J2 paracomplex structures of E. Suppose that these give a paraquaternionic structure such that H is adapted to this. Then N given by this is an H nilpotent structure of EH, and N star given by this is its dual H nilpotent structure. あれちょっと、こうしようか。This talk has just finished. Thank you very much.
Thank you very much for this presentation, Professor Ando.